Hello, everyone. Today, I would like to introduce our new work, Scalable and Serializable Network Multi-Actor Programming. I'm Bo-san, graduate from Purdue University. My advisor is Professor Petri Eugster, and we also have co-authors Gustavo Petri, Srivatsan Ravi, and Pierre-Louis Roman. Actor model is quite popular in cloud community in recent years. I think it is because it can provide excellent scalability, and many of them can also support elasticity. In an actor cloud application, actors are distributed across multiple servers. The client will send a request to an actor. Then this request will access more actors during the execution and finally return to this client. However, cloud applications have to handle hundreds, even thousands of concurrent requests at the same time. So assuming another request land on a different actor, but during execution, it accesses the same set of actors, then it is returned to the client. In this case, programmers need to reason about the execution of those concurrent requests on the same set of actors. Furthermore, cloud applications have to handle varying workload. After a while, assuming more and more clients start to send requests to your cloud application, then your application is overloaded. So you need to add more servers and scale up your application. However, your application must be scalable. Otherwise, even with more resources, your application cannot handle more requests. Now let's have a look at what kind of program model the cloud programmers may lead. At first, scalability. Their program model must support scalable network distributed programming in a mainstream programming model, for example, C++. Secondly, their model can enforce consistency, also called serializability, between concurrent requests when those requests are accessing the same set of vectors. The third one is dialogue. So their program model can relieve programmers from manually locking implementation in a distributed environment. There are also already several approaches to help programmers to implement the cloud applications. At first, let's look at actor programming language. So Akka is quite popular in recent years. We found it provides excellent scalability and performance. However, it don't support serializability at all. Olis is developed by Microsoft. It indeed provides transactional mode. However, we found its performance and scalability is quite limited in transactional mode. Except programming language, programmers can also implement cloud applications based on some distributed stores. Infinispan is a key value store. Programmers can put operations on key value data into a transaction body. Those transactions will be executed in parallel. However, when there are complete update, those transactions have, at least part of the transactions have to abort. Hypertext swap will organize data as tables. Because of this organization, it is limited to implement some applications. Then we have designed and implement a new actor programming model here. In this work, we are more care about the scalability and the serializability of the cloud applications. We have another work called Plasma, which is handle the dynamic placement for the actors. Plasma is published on URSS this year. Similar to other actor model, in AEON, actors are distributed across multiple servers, and those actors are organized as a directed acyclic graph through the ownership. We will have a detailed introduction to ownership later. So the client will send a request to an actor. This request is also called event in AEON. After this event is finished, it will use the callback method call return to the client. In AEON, event can also access multiple actors. For example, one event land on an actor. Later, he can access other actors through the ownership by calling sync on the or async method calls. After it's finished, it also uses callback method calls return to the client. Okay. Next, I will introduce why I will using game application to introduce the syntax of AEON. So assuming there is a steak house, multiple cooks in this house will make steaks on grills and serve their customers. The grills are shared by those cooks. Then the programmers need to avoid this condition and dialog when cooks are using grills. So in AEON, you can use keyword act class to define or actor type. Then you can use the create actor API to create a new actor from an actor class. So actor is a container of objects and the local variables. You can define the objects in the fields of actor class. In AEON, you cannot access the fields of actors directly. Instead, you can only access the actor through its method. In AEON, there are three important method calls here. So on client side, you can use event method call to issue an event to the cloud applications. The execution of those events will be serialized in the cloud application. One event can access children actor from parent actor by calling sync or async method call. So sync method call is similar to normal routine. It will block calling until it is finished. But in some cases, programmers don't want to wait for one method is finished. Then you can use async method call here. Then async method call will not block calling and will execute it in parallel. As I introduced at the beginning, actors are organized as directed acyclic graph through their ownership. So in this example, we have 4 actor classes here. Then we create 6 actors from those 4 actor classes. So in actor classes steakhouse, there is a field cooks, which is of type cook, and also field customers, which is of type customer. Then we say there is ownership between steakhouse and cook, steakhouse and customer. Assuming we create a steakhouse actor models. In the fields cooks of models, it have reference to cook actor Mac and Bill. In its fields customers, it have reference to customer actor Bob. Then we say there is ownership between those actors. Similarly, in actor class cook, it have fields grills and customers, which are of other actor classes. Then we say there is ownership between those actor classes and actors. However, in AEON, event can only access actors through their ownership from top to down. But in some cases, we want to make the method call from children to parent. For example, when the steak is ready, the grill need to inform cook. Then, so we introduce a yield field here. So yield field will not create ownership between actor classes or actors. However, so you cannot make the sync or async method call on a yield field. You can only make the event method call on a yield field. This will create a new event. Well, this new event will be dispatched when the current event is finished. Next, I will introduce the event synchronization protocol in AEON. At first, I will introduce some important concepts here. So Dominator actor is used to serialize event execution in AEON. We say one actor is a dominator if and only if it does not share any descendant actors with other actors, exclude its ancestors or descendants. So in the example, actor A, C1, C2 are dominator actors. B1 and B2 are not, because B1 and B2 share actor C1 and C2. So we say one actor A is B's dominator if and only if. First, B is not a dominator. Second, A is closed dominator actor to A, to B. So in the example, B1 and B2 dominator is A, because B1 and B2 are not dominator and A is a closed dominator actor. And actor is, for a dominator actor, it is dominated by itself. So each dominator actor have a dominator region, which is a set of vectors. It includes two types of vectors. So vectors dominated by A and A's closed descendant dominator actors. In the example, A's dominator region include all 5 actors. A, B1, B2 are dominated by A, and C1 and C2 are descendant dominator actors to A. So, okay, then let's look at the event synchronization protocol in AEON. So assuming there are 3 events, E1, E2, E3, which will land on actor C1, C2, C3. Clearly, B1 and B2 are dominator actors, and those are their dominator region. E1 and E2 will lock the dominator actor at first. Here we'll assume E1 is before E2. Then E1 will lock C1 and E2 will lock C2. However, E1 can access D1 and D2 from C1. So he will lock D1 and D2 at the same time. Then E1, E2 have to wait until E1 is finished. Then they can lock D1 and D2. Similarly, E3 will lock dominator B2, and then he will lock C2, C3, and D3. So because E1 and E2 are executing in the same dominator region, then their execution will be serialized on D1 and D2. But E3 is executed in a different region, so they can execute it in parallel completely. In the evaluation, we try to answer several research questions. We have compared the AEON synchronization protocol with the 2-phase locking. We also try to manually implement the synchronization locking mechanism in some actual programming language like ACA, which is and then compare with the AEON. We also compare AEON with consistent data store like HyperDex, WAP, and Infinispan. And we also compare with the actual programming language, which has the serializability support, like OOPSLA. So then we have measured the scalability of AEON on different number of servers, different types of method calls and the back sharp. And also we measure the fault tolerance overhead of AEON. So here in this talk, we only want to talk about the performance comparison between Infinispan, OOPSLA, AEON, and also measure scalability of AEON. At first, let's look at scalability of AEON. So we deployed our applications on AWS M1 small instance, and each server will have the same number of actors. So we use 2 type of events here: update events, use event, which will update the actors; change event will update the ownership. So we have 4 types of workload. Each workload have different percentage of use and change events. So as the figure shows, we're varying the servers from 2 to 32, and the only AEON application shows excellent scalability. And then also found with more user events, the performance is better because change event will up the ownership and lock the more actors. So in the evaluation of comparison among AEON, Infinispan, and OOPSLA, we deploy, then we fix the number of servers. And varying the number of cooks in each stake house. The workload is still same as the previous experiment. So as this result shows, in most cases, AEON outperform Infinispan and OOPSLA. So in Infinispan, if there are more cooks in a house, there is more complete update, then the performance become worse. So the for OOPSLA, the performance is limited. And we also found if we implement this application without with long transaction mode, the performance is much better in OOPSLA. Then let's look for the conclusion. So we have introduced a new actor programming model, AEON. AEON can provide scalable, serializable, networked multi-actor programming. So we have compared AEON with various actor programming language and the distributed store. And in most cases, AEON shows better performance. So about future work, we are planning to conduct the language usage study. Then based on feedback, we can improve our model. And also we consider to implement some new features like a future calls. Then we can combine the sync and async method call together. Thanks. This is our talk.